Hi, good day. Welcome to the fourth lesson in this Go playlist. We'll learn more about the integer data types that we introduced earlier in the Go data types video. So today we'll be talking about data type int. So we'll shed more light on the integer data type and its variants, the data type unsigned int and its variant as well. We'll be briefly showing some stuff about the related data types, that is the rune and bytes. I talked about this in the string data type dedicated video to that. Then lastly, we'll be doing a code illustration. Data type. The int data type is used to store positive and negative integers, that is non-decimal or numbers without fractions. Examples, we have 180 minus 45005 8492. We have many variants of the int data type, such as the integer 8, the int 16, int 32, and the int 64. If we try to store at any point in time, if we try to store a fractional number, let's say we are trying to store a float value in an integer type, it will be dropped off because it's not what it can take in. It can only take in integer values, number without fractions. So one thing to be aware is the first bit in the int data type is used to store the sign of the value, and the rest of the bits are used to store the value itself. Then we should take note in Go, when we use int, that's just int alone, it is platform or architecture dependent. It differs in languages like Java or C#, where int is usually a 32-bit as an ordinary value, but in Go it is platform dependent. On 32-bit systems, integer values are stored as int32, while on 64-bit systems, integer values are stored as int64. Most recent computers now work with int64 architectures. Most personal computers that we use, our laptops, our desktops, if it's very recent, most likely it's 64-bit architecture. Though we still have 32-bit architecture, more like older systems or older variants, which shows these particular differences. Here we have a table that shows the data type int. We have the int 8, which is being described as all signed 8-bit integers, and it varies from -128 to 127. We have the int 16, which is all signed 16-bit integers from -32768 to 32,767. Then we have the int 32, which is the 32-bit integers. It has a small, to some extent, a wide range of magnitude of value, but we should take note that in this we are storing values both in the positive line and in the negative line as well. And lastly, we have the int 64, which is a all signed 64-bit integers. I'm not sure I can pronounce the numbers, but it's very large and it has a wide range magnitude. Next, we have a calculation to calculate the minimum to the maximum value of an int data type. Remember, it stores value both in the negative side, and then I see it more like a number line. The formula is -2 raised to power bracket n minus 1, everything that's inside bracket, to 2 raised to power n minus 1, close the bracket, then now in the normal line -1. There are some concepts we need to understand while working with integers or even computers generally. A very good topic is the binary system. So we know binary is what the computer understands. Computer doesn't understand our normal English language or other languages that we speak. So the concept I want to introduce to us is the bits and the sign. So every integer in memory is stored as a sequence of bits, that's zeros and one. In unsigned integers, which is what we're treating presently, all bits represent values. Example, 8 bits, that's 0000 to 1111, that's to the end, that's 255. While in signed integers, the first, which is the most significant bit, is used to store the sign. And we should remember that 0 stands for positive and 1 stands for negative. In Go and almost all modern languages, they use the concept of 2's complement to represent signed integers. This system makes arithmetic very fast on our computer systems. So when you add a number, the computer is so fast before even you as a user can even think about how the computer do it. Computer is so fast because all these things, it works at a lower level, making it much more efficient when it's doing its calculation. For example, positive numbers, that's for the 2's complement. Positive numbers, they are stored normally in binary. So let's say we have a number like 7, we store it in the binary number. While negative numbers, it takes an absolute values binary, flip the bit, then add 1. So it's more like a 2 or 3 steps process. For example, on the screen here, we have number 5, and number 5 in the binary system 0000101. So when we have the value, we take the absolute. The absolute is now minus 5 from our O-level mathematics. Then when we write it down as the binary for 5, which is number said earlier, we flip the bits. That means we just sort of get the opposite of the binary numbers. So we have 111111010. Then after we had 1, so 1111011 is now how minus 5 is stored in the computer system. But there's a caveat to this because it works for all except the most negative values. So if we're to do for 120 minus 128, there will be an issue. It won't follow this 2 complement issue. It follows it, but there's a term which is used to define it, which is asymmetric. I don't want to bother you with all those for now because it might be complex to understand, but it's good to have background knowledge of how some of these things work. Next, we have the uint data type. It is used to store only positive integers, that is non-decimal or numbers without fractions. Example 160, 46,005. We have 8,492,792,578. We have many variants of the unsigned int data type, such as the unsigned int 8, unsigned int 16, unsigned int 32, and unsigned int 64. So the more the values increase, so from 8 to 16 to 32 to 64, there's a significant amount of increase in the magnitude and range of values that it can store. Also, all the bits are used to store the values, hence no sign is involved, making unsigned integer has higher values than the int range. We'll be talking about some other related data types. So we have the byte. Bytes represents raw data. So most of the time when you'll be dealing with bytes is when you're dealing with network protocols, when you're dealing with file systems and network interfaces, or to some extent memory optimizations. Then we have the range is alias for int 32. Most of the time is very related to strings, but most of the time range are used to represent Unicode because they cater for it better instead of using let's say a byte value to represent it. We have the unsigned int and the int. The unsigned int, if we take notes, doesn't have the number system attached to it. So an unsigned int and a normal int, they are both architecture or platform dependent. And what do I mean by this? If your system is much more recent, 9 out of 10, that means your system is a 64-bit system. So any integer value, it will be stored in the range of int64. That means you can work with numbers from the range that int64 allows you. And if it is an unsigned int as well, that means it works with uint64. But if your system is, or you're working on something lower or a bit of older system like 32-bit systems, then the unsigned int will be that of the 32-bit for the system, and while for int it will be for the int32. So they are architecture dependent. And languages like Java, I think I already mentioned that, and C sharp, they are integer, naturally they are stored as int32. Usually we'll use the uint or int instead of the size specific ones because they will fulfill most of our needs. If the value we are storing in a data type is less than or surpasses the maximum, it will lead to an overflow error. Hi, welcome to the code illustration segment of the integer data type. So basically we'll be doing different types of the int. So we'll be testing with unsigned int, small values, big values. It's going to be a very quick session since we already have a broad understanding of how everything is. So my first variable, so this is a small value of uint8. Remember, uint8 takes values from 0 to 255. So if I assign this value as 15 and I print it to the console here, that's small value, we can see that there is no error and this will compile fine. But in a scenario where okay, let's just test this so everybody is on the same page. In a scenario where I put in 256, the compiler is going to complain because the range of values that I'm putting now, it has exceeded the range it can allow. Remember, unsigned int 8 can take in from 0 to 255. So I'll be putting this, let me put it at the last value. So to test another, so these are for type uint8, that's just the comment there to guide us. Then another thing I want to do, I'll be doing the one with the negative sign. So var negative value, which is of type int8. Now remember, int8 can take in values from 0 to minus 128 to 127. So negative value equals to minus 23 minus 28. So to do this, I can fmt.println, so negative value. I'm going to print this out to the console so everybody is following along. Now remember, for you int 8, that means the range of values I can put inside this variable is from minus 128. So what if I decide to go a bit backward, that's minus 129? You can see that the compiler is complaining, but if we put it at minus 128, it's fine. And we can also put it at 127, which is the range of values. If I add just one value to it, it's going to cause an error, so the compiler is not happy with it. So basically I'll revert this back to a negative value. Okay, we've tested it earlier. Let me clear my console. Now this, we can just add a comment to LZ type int 8. Now the next thing is, how can we change from one value to another? But for you to change from a value to another, they must have like an intersection, or they must overlap in one way or the other. So for example, let's say I have a variable. Most of the times we'll be using this in our code base in 64, at times when you use a typecast, but most especially in 64 is better to use. So but when you're on a system, for platform dependency, on my system, mine is a 64-bit system, so by default my hint will be in 64. So if I have this var int normal variable, and I want to store the value of this small value inside it, something definitely will happen here, right? Int small value is equals to, so I wanted to declare it first, so I don't want to do normal creation and assign. So if I equate the value of this here, something just happened. So what happened just now is what we call typecasting. So for you to be able to do an effective typecasting, they must overlap, just like I said earlier. So we have this variable normal variable, and by default underlying system architecture is a 64-bit system. So this is just like a wrapper that says, oh, this my OS should determine the type, the underlying data type that it's going to be having. Then since int 8 and int, they sort of overlap in a way, because they are both integers, right? And definitely an int 64 definitely can take in values that contains unsigned int 8, because an int 64 has much more larger values, and it encompasses all numbers that you int 8 has. So now I'm putting the small value, which is 255, inside the variable for the int 64, but because Go is very strongly typed, it's still needed to typecast it to conform to the type of this, so which is very very good, because some of these things, the way the typing check for Go works is very very strict. It doesn't just allow anything. So I'll be running this again. We can see we have the 255 and it's working very fine. Another thing we can test is the concept of byte. So let's say we have a byte, my byte variable, which is of type byte, and so my byte variable, I'm assigning the value this. Well, let's use this. We can use it. So there should be something coming up in your mind, that how am I able to save, like call it a string? Remember in Golang, this is not a string, this is a literal, and it's usually used for bytes, for runes, majorly used for runes. So if I print this now to the console, we'll see, instead of having this value, we'll be having the value of this thing, which is an integer value for a, and this is like an ASCII code, an ASCII character. So small letter a is 97, and if we can recall, our big letter a should be 65 also. So because the underlying data type of type byte is same thing as uint 8, that's why this is very very possible. Then another one is my run var. Remember, run is what we use majorly in doing ASCII characters and all these Unicode values. So if I want to save a value there, my run variable, what will I have? Let's save this as a run. Definitely it should work because our run is int 32 by default. And remember, letter B is about what? Letter B will be 66, right? So if I do this and print it out to the console, we'll see letter 66, which is very good. Though this we can do this being that we are aware of the overlapping data type that a particular value can hold, a particular type can hold on or have. But one of the main use of runes is actually to store characters. Do I want to get the character? Control command space. So I want to save this particular character. You can see. So if we try to print this to the console, we can't get this. We won't be able to get this character because the underlying data type is int 32. Yes, so the reason why we are having 128513 is because it's being represented as an int 32 value. We can see to us this seems like a single character, but we should remember that runes can store values. It can store a value from about range of 1 to 4 bytes depending on how big that particular value is. So let's say I want to actually print out the the character that we have. So that will be the Unicode, the rain with the sign. Let me put stars with our inject it here on a new line, then pass the my run variable. So this our smiley will come to the command line. Let me clear the console. So we can see by default runes, when you definitely work with them, is as if you are working with the integer values beneath the hood, but we can still sort of check and look into it that, oh, I want to actually see this as a rune. So this is where this stuff comes in. Since we treated strings in the previous episode, so you can check this just string formatting. This is how to format it. I'm formatting it to conform to what I want to see on the command line. Thank you.